Okay, so inspired by what we were talking about a moment ago, I want to shift to egg drop mathematics. It is all that it's cracked up to be. So I did not create these slides. Unfortunately, the few moments we had between things. Okay, good. It's working. Okay. So hopefully things will work. Okay. Okay. All right, so here is how the problem is initially stated. We have a building with n floors, and we have 2 golden eggs. These are very special eggs. They will break if you drop them from too high of a height. If you drop them from below that height, it doesn't matter how many times you drop them, no damage is done. And you want to figure out what is the highest floor you can safely drop the egg from. You do not care how many eggs you have left at the end. You just want to figure out what's the highest floor you can drop it from. Okay?
You only have 2?
You only have 2.
Okay.
And you want to do it in as few drops as possible. So what do you think I mean by when I say as few drops as possible?
Few attempts as possible.
Few attempts.
Before you lose one or both eggs.
Well, do we care about losing 1 egg?
Say it again?
We don't care about losing 1 egg. We only care about, do we figure out the floor? I can have no eggs left at the end.
You may only have 2.
Even though I have 2. So let's say that it's floor 15 where that's the highest floor I can drop safely. And I drop my first egg at 14 and it doesn't crack. I then drop it at 15 and it doesn't crack. I then drop it at 16. Cracks. Okay, I know it was 15 and I have 1 egg left. I could drop the first egg at 16, it cracks. I dropped the second egg, let's say I dropped the first egg at 20, it cracks. I dropped the second egg at 16, it cracks. I'm dead, I've lost. I dropped the first egg at 17 and it cracks. I drop the next egg at 15 and it doesn't crack. I then drop an egg at 16 and it cracks. Okay, I know 15 had to be the highest I could do. And in that case, I would have no eggs left. I don't care how many eggs I have left. I just care what's the highest floor I can drop it from safely. And I want to do it in as few drops as possible. But again, we all have blinders on us. And so I'm not telling you how the floor is chosen, which is the magical floor where it breaks. So one possibility is maybe I choose something randomly from 1 to n. Or maybe a lower floor is more likely than another. Maybe a higher floor is more likely than a lower. And so you don't know the distribution of which floor it is. What kind of strategy might you adopt?
I thought of going half of n.
Okay, that's a strategy to try to figure out how you want to drop it. Right. So I guess what I'm trying to say is, when I say something as few drops as possible, do you mean the worst case? Do you mean the average case? So for instance, if you assume that the eggs are uniformly distributed among the floors 1 through n, you could adopt a specific strategy so that on average, this runs pretty well, but is occasionally very bad. Or you could be very concerned about the worst possible case. Well, what if the floor where it breaks for the first time is very carefully chosen to make my strategy work poorly? I might want to then adopt another strategy which isn't as good on average, but has much less exposure. So just very simple phrases such as few drops as possible, it's not immediately clear what that should be. Do you want to try to minimize your worst case? Do you want to try to maximize your best case? Right, that just means that the video from a few minutes ago is now ready to be uploaded, which I will do later today. So hopefully by now you've seen that we don't like hard problems, we like easier problems. So rather than having n floors with 2 golden eggs, what do you think would be an easier problem?
1 egg.
1 egg, right? And so I wasn't planning on talking about this, so I gotta do the slides on this one. All right, so we talked about interpreting, and then the easier question is, what is the easier problem? And you just said it, we have 1 egg. So I claim that there's only one strategy that you can do if there's one egg. Where do you have to drop the egg initially? Lowest. So you have to go 1, 2, 3, 4, dot, 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 dot. There's no other strategy that you can do, because if you drop it on 2 and it breaks, you don't know if it's 1 or 2. So worst case is, n drops. And I'm putting n in quotes because this is a public discussion amongst ourselves. I don't want to nitpick little bits of algebra. Is it n? Is it n minus 1? Right? So it's about n. Maybe it's n minus 1. I don't really, are we all comfortable with stuff like that? So we've now analyzed the case with just one egg. So if we have 2 eggs, once the first egg breaks, what happens? We do this. So we know that as soon as the first egg breaks, we go into the 1 egg game. If we had 3 eggs, as soon as the first egg breaks, we go into the 2 egg game. Okay, so the only possibility is to go 1, 2, 3 till it drops. Worst case is n drops. So now, once 1 egg breaks, we go into the 1 egg case. Where do you want to drop the first egg? What strategy would you like to use? So there's a couple of natural.
Halfway not appropriate.
That's a possibility. So 1 is halfway.
Half of it, and divide by 2.
So like a binary search.
Because that reduces the greatest amount of possibilities.
So that's great. So if the egg survives the first drop, that's great. What's another strategy somebody could do? You could do a third of the way. What else could you do? Going even more extreme.
One at a time again?
I'm sorry?
One at a time again?
So if you did it 1 at a time, then you gain nothing from having 2 eggs.
You have all top 4.
So instead of 1 at a time, what's a little bit better?
2.
2 at a time. 2 at a time.
Drop both eggs.
Well, there's no reason to drop both.
Like, wait, what's 2 at a time mean?
Second,
Floor.
fourth, fourth.
Oh,
Yeah.
the other one's
Yeah.
third mark.
2, 4, 6, 8, 10, dot, dot,
Oh,
dot.
sorry, I get it.
Yep. So I would say that those are the 2 extreme cases. And your third is you're trying to compromise, between, and you be a peacemaker, which is appreciated. So what are the possible strategies? So the extreme cases is drop every second floor, drop every n over 2. More generally, you could drop every x, where x could depend on n. And let's try to analyze this. So if we do, oops, I think that might have been an extreme zoom in, yes. This time I noticed. Okay, so drop at n over 2 and do a binary search. What's the worst thing that could happen to you if you do it every n over 2? Breaks immediately. Because if it doesn't break on the first try, you've eliminated half of the floors, and then the next one, you can eliminate another half. So worst case scenario, breaks, and then have to do like n halves minus 1 drops.
Can you give an example of, I'm sorry, I'm.
Sure. So let's say we have 100 floors. Drop at 50 and breaks. Now 1 at a time, 1, 2, dot, 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 all the way up to 49.
Okay.
So if you drop it on floor 50 and it breaks, then you're stuck doing 1 at a time.
Right, okay.
If it doesn't break, if drop at 50 and okay, then do 75. And if it breaks, you have to do 51 to 74. That's much better. So the worst case for you is going to be if it breaks initially. If it doesn't break, you've eliminated half the possibilities. So worst case, the number of drops is basically 1 plus like n halves minus 1. It's basically n halves. I'm not worried, I'm not gonna get the plus or minus one right. Okay, people wanna leave at 3, they don't wanna see the algebra at that fine of a level. Is everybody comfortable with that? Let's compare this with the every 2 strategy. Drop on evens. What's the worst case scenario now?
For 50 drops, right?
Yeah, is that basically, it's okay when I drop it on 2, it's okay when I drop it on 4, it's okay when I drop it on 6, it's okay when I drop it on 8. The worst case scenario now is it's okay when I drop it on 98, it breaks when I drop it on 100. So worst case is you have n/2 drops and then down to 2 floors, 1 more drop. So it's basically like n halves plus 1. It's basically also n halves. So in those 2 extreme cases, they're basically about the same. If we did every 4th, how bad could that be? So if we do it every 4th,
We dropped it 25 times, right?
so if we do it every 4th,
So
is
you-
it n/4 drops initially? Or is it 3n/4? How many drops do we have initially? If it's 100 and we do it every 4, that would be 25 drops.
Yeah.
And then we would have to then do n/4 after that.
Right. For the middle parts.
Wait, why n/4 for the middle part? Like if it breaks at like 80, but it didn't break at 76.
So it would be, no, sorry, it would be like 4 drops.
Okay.
Right, sorry, it'd be like 4 drops.
So, wait, you're, sorry, I'm trying to picture this. So with every 4, you would take an egg at 25, and let's say.
No, every 4 would be 4, 8, 16.
But you're not sure, but the initial step is doing it again 25, 50, 75.
Well, if you,
Isn't that what we're doing with fourths?
okay, so yeah, right.
So.
Okay, so then if it breaks, then we would have n/4 drops after that.
Say again? Sorry. I thought
So-
we were gonna
so-
No, you're talking about dropping it every 4th floor, right?
You're talking about.
Every
Separate.
fourth-
Two
every
independent
4th floor.
cases.
I thought, sorry, okay, my bad.
So every 4th floor.
Okay.
And so how many drops would that be? So worst would be n/4 plus 4.
Right, yeah, okay.
It's pretty similar to those 2 cases are. That's really nice. That like the
Right,
25.
but which is better, every 4th floor or every evens or halfway?
Every 4th.
Every 4th is better. Let's do every 10th. What do we get? We would have n/10 plus 10. As long as n is big, is this better?
If n is really big.
Yeah. So what's nice is the 2 strategies you came up with are in some sense the worst possible strategies. Well done. But I mean, those are the 2 natural things to do. They turn out to be bad. But there is a great life lesson here. Sometimes these mistakes can be used and fixed. So there were good ideas behind both of them. The first one was, I want to try to drop very far down the line because if it's successful, I eliminate a lot. The other one was, yes, I understand that, but if you miss, you have a huge thing to check. I'm going to be slow and steady, very incremental, but once I get a crack, I really have it localized as to where things are. So these are 2 extreme situations. Maybe there's a way to combine them into a new strategy. And given that I'm lecturing on this, I'm going to gamble that the answer is yes. And, it's going to illustrate some really good math concepts. Right. So this was basically the analysis we just did, that they're both basically of size n halves, but that's the worst case you can get. And so If we drop every x floors, we have n divided by x plus x, or maybe x minus 1. Right?
Yeah.
So this is a great example of competing influences. So when you look at this, give me a reason why you might want x to be large. Give me a reason why you might want x to be small.
The bigger X is, the smaller the whole total gets, because you're divided by it.
Good. So
Smaller X is, the bigger the whole total.
good.
The
So,
smaller the whole total gets,
large
because
X
you're adding.
makes small. Small x makes small. So we have two competing influences. One tells me to make x really large. The other tells me to make x really small. And we have to now somehow reconcile these two. Any thoughts?
Depends how big N is.
Depends how big n. So our answer should depend somewhat on n. How should we try to come to deal with this? So we have n over x versus x. If we make one large, the other becomes, I'm sorry, if we make one small, the other becomes large. So can somebody give me a possible strategy? It's okay if it's not the best thing to do, but something we might try to find a good value of x.
If I was breaking it up into that 100 floor problem, I would kind of keep going to see where it starts going down, that n over 10 plus 10 look good, and then keep going until it
So one thing is
starts
basically
going
to plot it and try to find, this is a function of x. We could set, f of x equals n over x plus x, plot this and try to see what value of x makes the smallest. So I know at least 2 people are teaching classes where you have techniques to do this. I don't know about your school districts. We don't have calculus in elementary school. I'm working on it. That one I can't understand being able to all. So how could we do this without calculus? We have n over x versus x. What might you do for those 2 terms? They're pulling you in different directions. What's something you could try to do for those 2 terms? They're competing against each other. How could you try to find an x that balances those 2 very different demands?
X is half of that,
X is half of what?
of N.
So one possibility is you could try x equals n halves. So if you take, try x equals n halves, that's going to give you n divided by x would be 2 plus n halves. So that's a lot larger than the previous step where we had n over 4 and n over 10. So it's not a bad thing to try. But x is going to be a function of n. So it's not immediately clear what the rule is, but we have 2 different terms. What could we do to try to make them comparable? If x gets large, the first term gets small, but the second term gets large. If x gets small, the first term gets large and the second term gets small. So we need to find a way to balance. We're being pulled in 2 different directions. What can we do to these 2 terms?
The average.
But what's taking the average mean? I have to find a value of x. So you have to give me a rule to get a value of x to try without using calculus.
That's the trick.
We did just do this in algebra 2 where we worked around. I was really excited we could use calculus. I honestly, it was the last year.
Right, so you have 2 different terms. What could you say about them? I want them to be equal. So try n over x equals x. Right, because then that's saying, look, we want both terms to be equally bad or equally good, depending on your point of view. And then that leads to n equals x squared, or x is the square root of n. And so this gives you some nice dependence. If you know calculus, if you take f of x equals n over x plus x, f prime of x is going to be negative n over x squared plus 1, f prime of x equals 0 implies x equals the square root of n. And then endpoints, f of n equals f of 1 is basically of size n. So if you take the extreme cases where x is 1 or n, you get something huge. And so if you know calculus, you get square root of n. If you don't know calculus, we can't prove that this is the best you can do, but it's not a bad start. It seems quite reasonable to try square root of n. And this is something you can do in algebra too.
Yeah, I think that's what I was upset, because there was no way to note that it was the best one, but also it was our quadratic geometry.
Right. And so you could plot this. And if you were able to plot it, you can basically make some kind of argument. But again, it's what's the most that you need? What can you prove? And even if I can't prove it's best, I can still prove that this is a really good strategy. And so square root of n looks pretty good. So if there's 100 buildings, whoever said 10, that was really good. And so, okay, so this was just doing the calculus, just so it's on the slides. Oh, lovely. Sadly, sometimes when I transfer things, it changes the superscripts and whatnot. This should be x squared. All right. So you can plot this. And so here's plotting it when n equals 100. And you see that there is some point, and it does look like it's 10. And then the next one I think is a better plot. Yes. Yeah. Okay. Yeah. So things got changed a little bit. Okay. So this is a really nice principle to think about. We had the function f of x equals n over x plus x minus 1. From the quick calculation we did, we thought x should be roughly of size square root of n. So let's change variables. We thought that square root of n was about the right thing to look at. So let's let let's let x equal t square roots of n. We're changing variables. And when we do that, the first term becomes n divided by square root of nt. So we would get, I'll call this function g of t, is going to be square root of n over t. And then the next term, x, is going to become t square roots of n. I can pull out the square root of n, and it's 1 over t plus t. And so now what I can see is, if I want to try to find the minimum, I don't have to do a different calculation for all the different values of n. I can sniff out the n dependence. And so even if I don't know exactly what the best is, I now have the right order of magnitude. It's square root of n. Whether or not it's square root of n, 2 square root of n, 1/2 square root of n, I don't know. But I know that it's of the order square root of n times some constant. It's whichever value of t makes 1 over t plus t as small as possible. There are ways you can prove that it's 1 without knowing calculus. But you now have a plot that's independent of n. So I love this problem. There's so much good stuff in this. And again, one of the big things, especially for those of you who are science teachers, is trying to pull out what depends on what. Can I pull out some of the other behavior and then be left with something else that's a little bit more universal and easy to study? You can do a lot more with this problem. So again, we could use calculus. And then you're supposed to get some good lessons, some good things to take out of this class. One of them is balancing different things and knowing where should you use something. So imagine we have 2 algorithms. The first always takes 1,000 seconds. You know how long it's going to take. This is commuting in Williamstown. Okay, I know what it's going to be. There is no uncertainty in how long it's going to take me to get my daughter to gymnastics. I know exactly when I can leave. There's a small variation. I mean, there's only 1 traffic light in Williamstown. I can avoid that. There are a few traffic lights as I go down 7. So there's a little variance, but not much. How many of you drove to Boston today? And how many of you left extra time? Hopefully it's, yeah, good. Everybody who raised their hand kept up because you don't know what traffic is going to be coming into the city. I remember once I had a meeting in New York City. I couldn't leave until I could get my kids to early daycare, and I drove down to New York City. And at the end of the day, they offered to validate my parking. I said, no, it's okay. No, we'll do it. It's fine. Yeah, we just have to go downstairs. I didn't park downstairs. Why didn't you park downstairs? Well, it was raining and the traffic was really bad. And I realized that if I drove all the way to your building, I would not get there on time. So I actually parked about a mile away and I just jogged around the last bit because that was the only way to get to you on time. So we want to balance everything. So the first algorithm is always 1,000 seconds. The second takes 1 second most of the time, but every once in a million, you get an input that takes, I think, 1 billion seconds. So on average, both take approximately 1,000 seconds. Which algorithm should you use? You can defend either or neither.
Who's the should, like, I mean, what's the stakeholder?
You.
But why do I care if it takes 1,000 seconds versus 1 second? Like, I'm worrying about my time?
So one thing is you might be worrying about your time. And again, if it's something that only has to be done once and you don't need it immediately, that's not so bad.
Right.
If it's something that needs to be done repeatedly, but if it takes 1,000 seconds, that could be a long lag. It protects you, but the probability is 1 in a million. And if you're only doing this 10, 20, 100 times, odds are you're not going to get that 1 in a million. So do you gamble?
It's like life insurance.
It's like life insurance. When I was in grad school, I didn't bother insuring my computer. I wouldn't like to replace it, but it's not a big deal. It's not going to make or break me. Most of us have house insurance because if that goes down, you're done. So in some sense, on average, both of them are fine. One of them has a really bad exposure that you could have a 1 billion second wait. But it's faster most of the time. So this, you can talk about mean, median, you can talk about variation, but there's a better solution. Does anybody see a better solution to just using 1 and 2?
Use the second one, but it takes more than a second. Switch to the other one.
Great. So use second if still running after, let's say, 2 seconds to be safe, switch to first.
Is there an interval? Like, if you got the 1 billion, does that mean that the next one can't be 1 billion? Or it's just as much probability the next one could be 1 billion? Like, is it like a slot machine?
Right. Yeah, I would say do it like slot machines.
Okay.
So that once you have that hit, you could have that hit again.
Okay.
But that's a great point because if you are like that, then once you have that hit of 2 seconds, there would always be use this for the next.
Yeah.
But notice if you do it like this, you get the runtime down to basically 1 second. Every now and then it'll take 1,000 seconds, but that will be or 1,002 seconds because you had that 2 second cost in the beginning. So this introduces the notion of switching, that you don't need to have a static strategy. And this is a huge thing I love to talk about, dynamic choices. So a lot of times people fix themselves into a strategy. So if you teach calculus and you do Riemann sums, the simplest way you do it is you make all the partitions equally spaced. But if your function is not changing that much, it's actually wasteful to be putting in a lot of observations here. You want a lot of observations where the function is rapidly changing, where it has a large f prime. And so it's much better to dynamically adjust how many points you're doing based on the rate of change of the function. If you're solving differential equations, same thing for stuff like that. And just you adjust based on what you have. And so this is just going through in details of what we're talking about, just switching between the two strategies. So it's possible to do a little bit better if you know triangular numbers, and I'm not going to go into too much detail right now. What you can do is you can don't drop every 10th if we have 100 floors. Drop the first one at 14, then 13, then 12, then 11. You drop a little bit further on the first, because if it breaks immediately, that's fine. It broke quickly. I didn't have to waste a lot of drops. And if you start a little bit larger and then you get smaller, well, if it took me more drops, that's okay now because I have fewer eggs left at the end. So you can actually do a little bit better than just dropping every X floor where X is the square root of n. If you have to do a fixed number of X floors, square root is the best you can do. But once the first egg doesn't crack, you've reduced it to a new game with fewer floors, with n minus X floors. So this is the dynamic adjustment. And again, part of what I'm just trying to do is just throw out some various ideas, but a lot of it is just the triangle numbers, just so it shows up on the recording. What if we have 3 eggs? Where do you think we should drop the eggs?
Thirds of the way up.
So one possibility is 2/3 of the way up. So the question is, what's the power of n? We have, with 1 egg, we did every floor, which is n to the 0. With 2 eggs, we did, keeps erasing. We did every square root of n, right? Which is n to the 1/2. So with 3 eggs, do every, so one possibility was n to the 1/3. Any other thoughts? How do you generalize the sequence with just 2 data points?
Into the 1/4.
N to the 1/4, maybe it's powers of 2.
It could also be 2/3. Because it feels like it should be larger than 1/2.
It seems like it should be larger than 1/2, right? So 1/3 seems to be too small. How could you rewrite n to the 0?
Sorry.
0/1. And n to the 1/2 is 1/2. So the next one could be 2/3. And again, spitballing here, right? We don't have enough to know. So we need to analyze 3 eggs. So let's say we drop 3 eggs at X. So worst case scenario with 3 eggs, drop every X. So we could have n/x drops. And then if that fails, then we have number of drops with how many eggs? We have 3 eggs. The worst case is that for the first egg, we drop it n/x times before it breaks. Now we have 2 eggs. And how many floors? So once the first egg breaks, we're dropping it every X. How many floors do we have to look at?
N minus X?
Nope,
Just
just X.
Right.
Just X floors, right? Because we're dropping it every X. So if it breaks, we then go up another X. I'm sorry, it hasn't broken. We go up another X, it breaks. It's somewhere between those with X. But we just showed before that when we have X eggs, we wanted to drop it at the square root. Well, we actually never analyzed it completely. So over here, if we drop it every square root of n floors, then the number of drops was n/n halves plus n/2 minus 1. It's about 2 square roots of n. We never recorded how many drops did it take. We just said, drop it every square root of n floors. We should have extracted that. Fortunately, I've given this talk before, and so I have extracted that. And so we know that if there are n floors with 2 eggs, it's going to take about 2 root n drops. And so now we go back to where we were. And so the cost is going to be n over x plus 2 square roots of x. And we want to find the value of x that minimizes this. So for those of you who know calculus, it's a calculus problem. If you don't know calculus, what could you do? You could try to plot, and again, we could play a similar game. We could maybe try to have x related to n and try to figure out what would be the power of n we want. And so divine inspiration, if I let x equal tn to the 2/3, then this becomes n over tn to the 2/3. That becomes n to the 1/3 over t plus 2 x to the 1/2 to the is n to the 2/3 is going to become n to the 1/3 t. Or is that t to the 1/2? I think t to the 1/2. Yes. So that would be n to the 1/3, 1 over t plus 2t to the 1/2. And if I do that substitution, I've now pulled out the independence. But if I don't see that, I have two terms. I have the n over x and the 2x to the 1/2. What can I do to try to find what is a good value of x to use? Set them equal to each other. So if we set n over x equal to 2x to the 1/2, that gives me n equals 2x to the 3/2. So x is basically on the order of n to the 2/3. I'm not worrying about 2 and anything like that, but this just tells me heuristically, I expect x to be of size n to the 2/3. If you use calculus, you can then figure out exactly what is the best thing. We saw that taking x to be like tn to the 2/3, that does give me something independent of n to analyze. And again, you were warned that there's going to be stuff at many different levels. It's okay if not everything is, but the idea here is breaking problems up into simpler ones and building it up. That's what we've been doing all day. And we started with the 1 egg, the 2 egg, the 3 egg. It wasn't clear what the pattern is. Gather more data. And as we gather more data now, we see that it is looking like 0 over 1, 1 over 2, 2 over 3. And if I had 4 eggs, what would you conjecture? 3/4. And so you can actually show that that will work. And this becomes great for the students to see how far can you explore. And if you know calculus, what's the best can you do? And then it starts getting messy as you try to keep in those constants. But if you just say there's some constant that works, I know enough to get the order of magnitude. What matters most is how things depend on n. And that's enough to get the independence. So I think that's all the stuff I really want to say. There was one more slide. Yeah. So what you can then do is you can then just try to get more and more data and try to make tables and see if you can sniff out the pattern, if you can say anything about what those constants are. But there's a lot of stuff that you can explore. And again, you don't need calculus to do this. But if you want to prove that you have something that's optimal, yes. The other thing is, this might be optimal with respect to one strategy, but maybe there's a better type of strategy. If I'm dropping it every x floors, this is the best I can do. But maybe every x floors is not the best. And in fact, if you use triangle numbers, that was the first sequence we looked at: 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. These are the triangle numbers because as you draw them, you get triangles. And that's the best you can do here. So you do it a little bit more in the beginning, because if it breaks, that's fine. You haven't done that many drops. So you're doing some kind of dynamic strategy. You're adjusting based on what happens. And this is something that's really not emphasized, I think, a lot in school, is that you don't just pick one strategy and say with it independent of what everyone is doing, is you start to see how are things responding. As an aside, we had talked about, summing odd numbers. So this is probably my favorite proof about why sums of odd numbers are perfect squares. So this is proof by picture. And I love that I have all these colors and I don't have to worry about erasing them as I would on any crappy board. I'll do one more level because I have to get to 3 o'clock. I'm joking, I'm joking. And so what you see is you go from one level to the next, all these stuff go down, all these stuff go over, and I add something new, but I also had a double counting. Right? So I had one gold was used twice. It was used to move to the right, it was used to move down. So the number of additions is 2. We always increase by 2 as we add the next thing. That's the next odd number. So this is enough to show us that the sum of the first n odd numbers is n squared. So sum of first n odd numbers is n squared. So what if I give you, again, I've never done this before. This is brand new. What if I give you 1 plus 2 plus 3 all the way up to plus 2n? And I want to figure out what that sum is. So I can write this as 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 plus 2 plus 4 plus 6 plus dot 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 plus 2n. So how many odd numbers do I have in the first group?
Two and minus 1 squared.
Well, how many odd numbers do I have?
Over 2.
Oh,
So how many odd numbers are there? Just n, so it's the first, so what's that first sum equal to? N squared. So this is n squared plus twice 1 plus 2 plus 3 plus dot 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 plus n. Because all those numbers are even. So if I want to sum all the evens from 1 to 2n, it's n squared plus twice the sum of all the numbers from 1 to n.
Why is the first one n?
N squared?
Yeah.
Because we have, over here, we have the first n odd numbers. And we show that the sum of the first n odd numbers is n squared.
But we ended at 2n minus 1.
Right. So there's 2n numbers, right? From 1 to 2n. Half of them are even, half of them are odd.
Oh, okay, right.
So this becomes, do you want to write your odd numbers as 2n minus 1 or 2n plus 1? How do you want to phrase them?
I get it with the 2n part. Okay, I got you.
So we know that sum, and now we have twice than the other sum. What would that sum be? And so if n was even as well, we could play the game again. So if n is even, lather, rinse, repeat. So if n is a power of 2, okay, we can just keep doing this until we get it all the way done. Unfortunately, when we try to play this game, it becomes a little bit hard. Because we are missing a little bit. Right? So in some cases, we would be able to make this work. In this particular problem, we've reduced it to a smaller problem, but it's unfortunately not exactly what we have. Unless we could somehow relate them So if I wanted to look at one, and again, hopefully this is showing you how a mathematician thinks, plus n versus 1 plus 2 plus n plus n+1 plus dot 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 plus 2n. Well, I see that this is equal to that. And now over here, what's the relationship between these numbers and the numbers here? Let's compare them one at a time. How would I compare, what's the difference between n+1 and 1? What's the difference between 2n and n? So if I call this sum here Sn, this is Sn, and each term here is n more than Sn. And how many terms are there? There's n terms. So this would just be Sn plus n times n halves.
Wait, what times n halves and not n?
Because I'm thinking of something else. You're right. Thank you. N times n, because there are n terms and each term is n more. So what we've just shown is S2n, which is 1 plus 2 plus dot 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 plus 2n, is equal to the odd terms n squared plus Sn. But we also showed that this the sum from 1 to 2n is equal to Sn plus Sn plus n squared. Did I make a small mistake somewhere?
I think it's n squared plus 2 less than 1, because it's 2 plus 4 plus 6 plus 8. Which is
Okay, good, good. Good. So, thank you. So, it should be a 2Sn here, I think.
Yeah.
Yes, that's right. We had 2Sn. Good. And so if we look at this, unfortunately, it perfectly cancels, right? And so if we try to do something like this, it doesn't help us at all. We end up just subtracting everything and we don't get anything useful for Sn. So everything is at least consistent, but we weren't able to extract a formula for Sn. I'm just taking a quick look to see if there's anything we can do here. Yeah, so unfortunately, this happens, sadly all the time. Is you try to do an argument, and you get into a place where everything cancels out. And there are other problems where you can do tricks like this, and it will work. For this one, unfortunately, it seems like the trying to count it 2 different ways just reproduced, sadly, an identity. How many of you have dealt with sums like this with your students? Okay. So with stuff like this, one of the things I really like to talk about is just trying to find upper and lower bounds. And just as an aside, for Sn, it's clearly less than n times n, because each term is at most n and is at most n terms. It's clearly greater than 1 times n, because 1 is the smallest number. But that's a really bad lower bound. The lower side is of size n, the upper side is of size n squared. They're too well separated. A better lower bound is there's n halves terms that are at least n halves. And now that gives you a lower bound and an upper bound that's of size n squared. So even if I don't know the answer, I at least now know order of magnitude. And so, unfortunately, it's not going to give me the exact concept, but it's going to tell me it grows like n squared.
Is that a similar concept like the squeeze theorem?
It's similar. So for the squeeze theorem, you want them to actually get closer and closer. And you can start playing games like this to get things closer and closer. And so what you could do next is, I have 1, 2, dot, 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 n fourths plus 1, dot, 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 2n over 4, dot, 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 3n over 4, dot, 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 n. And then if I want to try to get lower bounds, everything here, well, let's do an upper bound. Everything here is at least n fourths, and I have n fourths of them. In the next one, I have again n fourths terms, and each one is at least, is at most 2n over 4. In the next one, I have n over 4 terms, and each one is at most 3n over 4. And in the last one, I have n fourth terms, and each one is at most 4n over 4. So if I add them all up, I'm going to get an n squared over 16. Then I'm going to have 1 plus 2 plus 3 plus 4, which is 10. So this is now 10/16 n squared, which is much better than n squared. And that's much closer to the 1/2, which if you know what the sum is. And so you could keep doing this as a nice exercise and try to show that it converges. There's a really simple proof of what the sum is that goes all the way back allegedly to Gauss. The story is that, when he was in kindergarten, the teacher was just having one of those days and just wanted the kids to shut up. So asked the kids to add the numbers from 1 to 100. You're thinking that, okay, you'll keep the brats off my back for a little bit. And Gauss yells, a second or two later, 5,050. And what Gauss noticed, according to the story, is that if you write Sn as, I'll do it as 0 plus 1 plus 2 plus dot 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 plus n, and then you write the numbers backwards, n plus n minus 1 plus n minus 2 plus dot 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 plus 0. If you add them all up, you now get twice the sum, and each of these sums is going to just be n. And since we have n plus 1 of them, it's just n plus 1, n times n plus 1. And therefore, the sum is just n plus 1 over 2. And so that's a nice way of just dealing with sums like this. There are certain cases where you can play tricks like this, and you can sometimes extract formulas by knowing other things. And so I've got some papers with related sums. If you're interested in EBMA, where you can take knowledge of one sum and use it to get knowledge of another. It was interesting in this particular case that it just reduced to 0 equals 0. It's annoying, but it happens. So we've got a few minutes left. Is there any topic people are particularly interested or curious to see? If not, I will end with something for you to think about for the next class. And this is a application of like generalized Fibonacci numbers. So Fibonacci betting. And again, because this is being recorded, I do not advocate applying any of these strategies or gambling. However, is everybody roughly familiar with roulette? So you have a wheel, you have reds, you have blacks, and you have greens. And there's many different types of bet. The simplest is betting either red or black. And if your color comes up, you win. If your color does not come up, you lose. And we're just describing the basics of roulette for something to think about for. And I am not advocating that you gamble. Because there are two greens, you don't have a 50-50 chance of winning. Let's say we go to work. Okay, so we're going to play a simple game, a simplified version. So there's only two. There's you bet on red or black, 50% chance of either coming up. All spins, bets are independent of previous. So you will not get odds this good in the real world. In the real world, it's a little bit less than 50% chance of having a red come up. But we'll go to politicians, they will pass some laws, and casinos are no longer allowed to have greens. And so now you have to have a 50-50 chance of winning. And so the following strategy was used by many people, and it's called double plus one. And here's how it works. Bet $1 on red, if red, up $1, else down $1. If down, bet $2 red, if red, up $1, else down how much? $3. If down, bet $4 red, if red, up $1, else down 7, right? Yes?
Yeah.
Now what do we do? If down, bet how much on red?
8.
8,
Oh.
we're down 7, right? You bet $8 red, if red, up $1, else down 15. And then shampoo. Lather, rinse, repeat. Eventually, red will come up. Eventually, you win $1. Lather, rinse, repeat. Why am I not gambling?
I have infinite money.
That is the problem. I do not have infinite money. Not only do you need to have a lot of money, you need to have the stones to, you're down $1 million to place the bet. So one way around this is the eccentric rich uncle aunt hypothesis. You have a crazy family member who will stake you no matter what. You need $1 million for a bet, they're there for you. You want to borrow $5, hell no. I'll stake your bets, but I won't give you any money directly. So if you need $1 million, you have that available. Is that enough to work here? And for this, you actually need to know a little bit about how roulette is actually played. So does anybody know any of the house rules for roulette?
Like how you actually play?
What the house can and cannot do when you want to make a bet.
Like they can't touch chips when they're on the table.
But there's that, but let's say you go to a casino and you say, I want to bet some money. You bet and you lose. I want to bet more money and you lose. I want to bet more money.
Oh, they have
and you lose.
limits.
They have limits. They have maximum bets you can make. Trust me, mathematics is used quite carefully to calculate the maximum bet that they allow at a table. So you're in trouble if you get a large string of consecutive blacks. So the question is, this is the same as flipping a coin getting heads and tails. How likely is it to get a string of so many heads in a row? I'm sorry?
Not like.
Okay. But if you keep doing it enough
But it
times,
happens, yeah.
it
There's a
happens.
whole like, model that if you ask like a kid.
Yes.
To decide like out of 100 trials, heads and tails, you can tell who, I'll use like a kid as an example,
Yeah,
but probably
yeah.
an adult too, a non,
non-mathematician. Yes.
and you can see that the adult, the human, which one they made, because they will rarely have things that repeat more than like what 3 or 4 times.
Something
When
like that,
actually in
exactly.
100 trials, there might be a 5 or 6
Right.
repeat. So.
And so if people are interested, we can actually, this is something we can talk about in the next meeting. How do you actually analyze a problem like this? How can you do this with kids of young ages? How can you calculate what these probabilities are? And it's related to the Fibonacci numbers. So it's a generalization of the Fibonacci numbers that solve this. When I was a little kid, my dad heard about this. He goes, this is too good to be true. And so he wrote a computer program in BASIC to simulate this, and very quickly saw, oh. Now, if you think about it, most people could probably use a strategy like this and walk away with a small amount of money. When you win small. And every now and then, when you lose big. And one of the things Vegas did is, I've never been to Vegas proper, but I've been in airports and whatnot. And there's some brilliant marketing that goes on. And so for instance, in slot machines, when you win, they no longer spit out the money. Why don't they spit out the money? They want you to keep playing. It's an electronic credit. They do whatever they can. So this goes back to the earlier psychology part of today's seminar. In roulette, what they do in places is they display the last couple of spins of the wheel.
People say that red is due.
So there's two types of morons.
Yeah.
There's like, oh, red is due. It's been black a lot of times. Red is due. And what's the other type of moron?
It's on the street.
Red's on a streak. Red is hot. Go red.
Richard Cleary spent the entire first class last time talking about streaks
Yes.
and how that is not a thing. And it was so, there was a gentleman sitting next to me and he was like, you can't convince me of this. There's such thing as a streak. Like,
Right.
and at that point, I think the Celtics were on some streak like at that time. And we're like, no, it's not streaks. It was. Yeah.
Well, it's just when you have enough events going on, something is going to happen. And so, there's a huge discussion. Is there anything true clutch hitting in baseball or clutch shooting in basketball? Well, if you focus on certain people, they look really good. You don't focus on the people who aren't clutch, unless they're really not clutch and they underperform. And then you talk about your Alex Rodriguez and your Mr. May. With enough events, real things should happen. And so when I was on the job market, when I got the job at Williams, I was applying at other schools, and I'm going to get the city wrong possibly. I think it was Syracuse, New York. Barack Obama and Hillary Clinton exactly tied in votes. And there was a huge discussion about how unlikely this was. Well, it depends on which calculation you do. So Hillary Clinton won New York, I think, with 57% of the vote. So if you use 57% as your probability of a vote, that's quite unlikely. If you use 50%, there's about 1 in 1,000. There's a 1 in 1,000 probability unlikely. And they're not going to report on all the places when they don't tie, right? The one that makes the news is the tie. Well, how many cities were there of comparable size in America? They should tie somewhere in the primaries. I'd be surprised if they didn't. And so Vegas doesn't care which kind of math moron you are, that you think it's streaky and it's going to keep going, or you think it's due. As long as you put the money down, they're happy.
Even like the earthquake this week, like there's places that have earthquakes every day.
Right,
Japan,
right,
Alaska.
right.
Because we have, so it's not that rare.
It's not that rare.
We're actually on a phone line, but we used
If
to
you
go
predict
to-
ahead of time where the earthquake is going to be or how severe it's going to be, that's different.
Yeah.
And so the question here is, how likely is it to get, say, 5 blacks in a row and go bankrupt? If there's only 10 spins, it's not that likely you'll get 5 in a row. If there's 100 spins, now all of a sudden, maybe it's a significant probability. So that's something to to think about. This is definitely something we can discuss in detail. You can do some very simple Google Sheets to help the kids, even if you can't come up with the closed form expression, to actually calculate and see the probability. What should happen to the probability the more spins you have?
Probability of what?
Of getting 5 consecutive blacks.
The more spins you have, the more likely you are to get 5 in a row.
Yeah, it should get higher and higher and higher the further down you go. And so, again, I love problems where we can discuss things without knowing too much advanced mathematics. And this is very similar to something like that. We can also talk about the M&M game, which was inspired by, I'll say, a suboptimal daycare my kids were at when they were 4 and 2. And so I would pick them up early. And my son asked me once, if you're born on the same day as someone, will you die on the same day? I thought this was a really good question for a 4-year-old. How do you explain randomness to young kids? Well, my wife is identical to it. Look, Aunt Sarah's dead, but no, okay. That's not, it's a way, but it's not a good way, and it will lead to other complications. It would be the last math I could explain to my son for 15 years to life. So we came up with the M&M game. Everybody starts with an M&M and a coin. You go 1, 2, 3, toss. If you get a head, you eat an M&M, and if you get a tail, you don't. And you can try to calculate, if we start with the same number of M&Ms, what's the chance we eat our last M&M at the same time? And it turns out there's a lot of really good math related to this, and not surprisingly, it's related to some kind of generalization of the Fibonacci numbers.
Wow.
So my goal is to try to show you math that can be done at many different levels. I'm happy to work with you to try to convert anything we've done today or anything else to something that you could do in your classes. Your easiest, of course, is math, but we can definitely talk about how can you apply some of these problems in something
The
like chemistry.
probability stuff will apply to chemistry.
Oh, yeah. And then a lot of chemistry is the probability of having the molecules hit with the right orientation in three-dimensional space.
There's a lot of that, and then just early chem we're talking about a little tiny bit of quantum mechanics and electrons. Probably.
Yes.
And we do like to touch it so small.
Yes.
Smally. Clearly I teach you, but
Let me just stop recording.